So this is what we did. So what I've done in the last lecture, the Kenyon operator. Today what start is another thing that we require is the propagator for the electromagnetic field. So let us start with this, with the Maxwell's equation in the presence of source, and you know that this FU lambda is basically field strength tensor, and we want to find out the propagator for this field. So once again, the standard technique is the following. If you just expand this equation, this FU lambda, what we shall get is the following: mu a lambda minus del lambda. What I have done is I have substituted this field strength tensor in this equation, and this from this we get the first term to be of this form, box b lambda, where box is basically del mu del u, is the D'Alembert. Then we have del mu del lambda. That is equal to so if we have this now, we mu in the last term, and from here I just want to write this in this way. So mu is done, so I can just take this up and take this index down. This term I will write it following here: box of the and mu. So I write this term in this way. From here, what we shall get is the following: lambda mu box minus del mu del lambda d mu j lambda. So this is the operator that acts on mu. It is this, right? And what we need to do is the following: we need to find out the propagator for the electromagnetic field. So what we shall do is we shall write the Green's function equation or equation corresponding to this operator. So we have lambda mu lambda that is equal to lambda division 4 x minus x. This is here. So what I am doing is the following. So as I mentioned earlier, that any function which satisfies an equation of this form, operator acting on the function gives you a delta function, is basically the Green's function, right? So this is your Green's function, and if I know the Green's function, then you can at once write down solution of this inhomogeneous partial differential equation in terms of the Green's function. And that will be what? That will be obviously then you denote function of x. By 0, I mean that this is the solution of the homogeneous differential equation without the J lambda, and then I shall have plus d4 x prime x prime, and then J. So you can at once see that the solution to this partial differential equation, the inhomogeneous partial differential equation, is this in terms of the Green's function. Because if I operate both sides with this operator, this operator acting on this will give us 0. This operator acting on this thing will give us the delta function along with this Kronecker delta that you have here, and then you can perform the integral and you will get J. It is the same as we have been doing so far for the real scalar field as well as the Dirac field. It is the same. Only complication in the case of this electromagnetic field is that you have indices. This is the only complication that you have and nothing else. So that is why it looks a little bit complicated, because you have a flex over here, and therefore you have a tensorial object of this kind with two indices, mu, and then you have to come back with the J mu to get only one index. So we have this now, and our next aim is to calculate this object, this d mu. So if I can calculate this d mu, just put it over here, and I will get the answer for mu. Right? It's the standard thing that we have been doing. So let us try see how we can calculate this object. So once again, the standard technique is to Fourier transform this d mu, and now we just substitute this thing in this equation. And if you do that, what we shall get is the following. So when this operator acts on this thing, this will give us this object. This is basically eta lambda mu delta 4 d4 5 4
Sir.
Yes.
Sir, just as we used in the electromagnetic case, why aren't we using the del mu equals to 0 term? And that will simplify the calculation.
One?
The del mu equals to 0 value.
Oh, okay. This is a good question. See, this is the Maxwell equation, right?
Yes, sir. Sir, can you change the board?
Oh, you cannot see this part. So the Maxwell equation that I have already written down, this one.
Yes, sir.
Okay. Here, the analysis that we have been doing so far, we have not fixed any gauge. Okay. We have not fixed any gauge. So you want to do an analysis which is gauge independent.
Okay, sir.
Okay. But the thing that you are saying is that del mu is equal to 0. You can choose, you can work in this gauge, but we want to carry out, or we want to find out the propagator for the electromagnetic field without fixing any gauge or without working in any gauge.
Okay, sir.
That is why we are not taking del mu is equal to 0. Okay. But there will be a twist. You have actually asked an important question before. We shall find that it will be absolutely necessary, or it is an absolute must for us to fix a gauge or to work in a particular gauge. Otherwise, we'll see what happens in a moment.
Okay, sir.
Let us just proceed, and I have to just shift this board. So what we are doing is now we are substituting this Fourier transform dv mu in this equation. The right hand side of this equation is this, and this is the integral representation for the delta function. And now this operator acting on the right hand side of this will give us what? This will lead us to equal to 5, this will be 4. Then we have finger, prime. Then we have eta and w. Eta and w. The box, the renumeration will give us a minus of k square, right? The minus of k square minus del mu del lambda. Each of them will give us minus I. Del mu will give us minus I k mu, and del lambda will give us minus I k lambda when it acts on this exponential. So this is what we have. And if we compare both sides, because this forms a linearly independent basis, therefore you can equate their coefficients. If you equate the coefficients, you shall get eta lambda mu equal to d lambda mu a times where the lambda mu. This will give us a minus, this is minus plus a mu. So this is what we have, right? So what we have done is, you can just check the calculations later once you do it in your hand. So what we have done is we have substituted the Fourier transform for this dv mu and the integral representation of the delta function in this equation, and from that equation we have obtained a relation in the momentum space. And this is the thing that we have been doing so far. So now you can see the full board. So let me just write down the equation once for it. This is d lambda mu a minus a square lambda mu plus a lambda equal to. So that is what we have. Minus eta lambda mu. Now you see that this is a second rank tensor. The most general form for this second rank tensor that you can take the following. You can take it to be of this form: a eta mu is the second rank tensor plus b mu. Because you need to solve this equation. Once we solve this equation, then we will get dv mu tilde k. Then we can substitute it in the expression there. Then you know what dv mu is, and therefore you know what k mu is. So this is the answers that we take for d theta mu k. And let us now, where a and b, these are unknowns. We need to determine these unknowns. So we substitute this in this equation. To substitute it, we shall get the following results. Just check whether I'm writing down the indices correctly or not. Good.
So there may be no terms which combines vitamin U and K for lambda that indices may be concentrated. Like vitamin U, K, mu, K, mu.
Tell me a term.
So just be this.
Theta.
Eta mu lambda, U and lambda is substituted.
Theta.
Mu lambda. No, lambda is in U.
Okay.
K lambda, K mu.
K.
Mu.
K.
Mu. Mu means 6%.
This one. This is the K mu. Why are we giving this? Take anything. I told you that this is the most general form that you can take. You can try yours. See what happens. Take it. See, a very simple answer is to this question is the following. Should be as you expect this d tilde mu to be symmetric in mu. You will not want it to be anti-symmetric without any loss of generality. That is what you would expect. So that is why you want it to be of this form. Maybe there is a much better argument to this also. Maybe you can find a better argument. But I have to see. That is probably the reason. This is a symmetric term. This is a symmetric term. And what I was thinking is the following. See, here I have written it in such a way that this mu I have actually contracted, but this I have kept free. So this is lambda and mu are free. But if you contract that, here if I suppose I put a lambda, then and this is summed over, then this is symmetric in mu lambda. Without any loss of generality, this must be symmetric in mu lambda. Because if it is antisymmetric, then it is gone. Okay. So this is the answers that we take for d tilde mu k, and we just substitute these answers in this equation. And let's see what happens. So this implies that we have minus a square eta mu with eta lambda mu. That will give us what? That will give us theta mu and mu contract. So we will have theta lambda mu plus in minus b a square. This is a mu k mu. So this will give us a lambda k mu. Then we have plus a eta mu mu. This will again give us eta mu mu k mu k lambda. This will give us a mu k lambda. And this term plus b K mu, K mu. So this gives us a K square. Then K mu, K lambda. That is equal to eta lambda mu. By the way, you should remember that eta lambda mu, whenever this is a mixed tensor, it's basically non-effective. That you should always remember. Okay. Now, from this, you can immediately see that this cancels with this. And what else do we have? These two cancels, right? And this is also delta lambda mu. Therefore, if you compare both sides now, so here we have a delta lambda mu, here we have a delta lambda mu. So you compare the coefficients. If you compare, you will get minus a k square to be equal to 1. Right? Comparing the coefficients. And from here, we have the k mu k lambda term, there is no k mu k lambda term on the right. Therefore, a is equal to 0. Right? And not only that, b is undetermined because b has cancelled it. B is undetermined. There is no b in the equation. So the answers that you have taken here, you cannot determine this term because b cannot be determined. So you cannot determine it. And not only that, you get the value for a, you get a to be 0 and this. So it shows that a, the result that you get for a is inconsistent. There cannot be two different values of a from the same equation. So it is completely inconsistent. So it tells you, basically what this calculation tells us is that what can you tell? What can you infer from this calculation? From this thing that we have done. So our aim is to find out this, right? So what can you infer?
We cannot find it.
We cannot find this simple thing. So we cannot find this. So what does it tell us? The propagator does not exist. This is clear. The simple conclusion that we can draw from this calculation is that the propagator does not exist. That's it. Just a second, I'm just coming to you in a moment. Please. For photon field, that is what it turns out, that you don't have a propagator for a photon field. Then you cannot do quantum field theory. That you know ahead. Or photon is a boson, that you know ahead, that you are coming ahead of the story, and you already know that if the propagator does not exist, then it tells us basically that you cannot do quantum fields. But that is not the case. There must be a propagator for the photon. So this seems to be like a paradoxical situation. But why did we get such a result in the first place? The question is this: why did we get such a result? That your photon propagator does not exist. The people online, do you have any idea?
Sir, only because of the del mu del lambda term.
It is only not because of del mu. Which term? This term.
Del eta mu nu box minus del mu del lambda, the second term.
Okay, I see. No, that is not precisely the reason. The reason is connected to the question that you raised a little while ago. That you wanted to work in a gauge, right? And this theory, this thing that we have been trying to do, you know that electrodynamics is a gauge theory, right? So there are gauge degrees of freedom. And what these gauge degrees of freedom basically means is that there are unphysical degrees of freedom in the photon field. So what do I mean by that? This is the gauge field, mu, it's the electromagnetic field, and it has four components, A0, AI, where I comes from 1 to 3. But we know that the photon field, if I say that this is my photon field, because this is what we have quantized in the three electromagnetic field case, we have quantized this, and we have seen that we have got photons from by quantizing this field. And what we have seen there is the following. We have seen that electromagnetic field is a transverse field. So, out of these four components, this A0 component is what? This is the time-like photon. And this A3 component is what? This is the longitudinal photon, right? But we know that the photon field is a transverse wave. The electromagnetic wave is a transverse wave, and therefore there can be only 2 degrees of freedom. Only A1 and A2 are the physical degrees of freedom. A3 and A0 these are not the physical degrees of freedom. Why are there unphysical degrees of freedom in your photon field? Because this is a gauge theory. Whenever you have a gauge theory, there are unphysical degrees of freedom in your theory, and that is why this unphysical degrees of freedom is actually creating this problem. That you are not able to find out the proper photon field, photon property. But when you get rid of those unphysical degrees of freedom, and we have seen earlier that you can basically work in a gauge where A0 is 0 and AI is equal to 0. So this is the Coulomb gauge, right? We have actually quantized the photon field in that gauge. So what it does is basically it gets rid of these two unphysical degrees of freedom, and therefore you can really see the transverse nature of the electromagnetic field. And therefore, what we shall do now is the following: we shall try to work in a particular gauge and see what happens. So just before that, since we have already done this calculation, we have this equation, or rather we have this particular equation, theta lambda mu. Let me just check the equation once more. The equation that I've already written down earlier. So what we have is minus k square theta lambda mu. So this particular thing plus k mu k lambda d tilde mu a theta lambda. So you must be thinking, why did I write the equation once more? But I shall do one trick here. You see that when I took this answers that d mu function of k is a theta mu plus d a mu. This is the answers that I took for this unknown that I want to find. So this was the most general form that I argued you can take. What we found is that this b was undetermined from that equation and a was inconsistent. But now you can play a very simple trick. The trick is the following. Just modify this with this, and let us call this zeta. Okay. So what we are doing is we had this equation earlier, but now in place of this equation, we are putting a factor with this ku k lambda term. We are putting a factor of 1 minus 1 by xi. And suppose, or in other words, what we are saying is that instead of this factor being 1, this factor is not something which is not equal to 1. Some factor is some zeta. So we have just modified this equation. Please don't ask me at this point that why are you doing this. I'm doing it for a particular reason which you will understand just now. But you may ask that from where did you get this idea of just modifying or deforming this equation? I will tell you the reason. But let us see what happens if I do such a modification. And once again, I will put these answers here. Okay. And if you put these answers here, then you shall get minus k square lambda mu plus zeta a mu lambda. This thing is a mu plus b. Let us now multiply this throughout as we did earlier. This is minus k square, which are lambda mu, so I will get a k square. Lambda mu will give us lambda mu. Then here this term plus a beta a mu, so this will give us a lambda. And this gives us minus b a square. Beta lambda mu is a lambda mu. And then the last term is multiplied by this plus b zeta a mu, so that gives us a square. Then we have k lambda, and that is equal to once again beta lambda mu. And now let us see what solutions can we get from this equation. So this will give us beta lambda mu minus a k square, the first term, all the terms are k mu this minus sign. Then we will have plus a lambda a mu. And now collect the solutions, all the terms. A lambda k mu, this will give us a zeta first term. Then we will have a minus b of k square. Then we have plus square zeta, that is equal to the lambda mu. And now you can immediately once again compare the coefficients beta lambda mu. So this gives us as before minus a square equal to 1. And from this part, this second term, we don't have a k lambda k mu term on this side, but the coefficient of this term must vanish. Therefore, we have another equation, which is k zeta minus b square into 1 minus the equals 0. Okay. So let me just check whether I have this correctly. From here I get a to be equal to minus 1 by k square. Solution for a is this. And if I substitute this solution over here, I should get the solution of b. So this gives us a consistent solution. So let us see what do we get here. A zeta minus 1 minus, okay, let us just simplify this term. So 1 minus zeta is equal to, zeta was what? Zeta was this thing, 1 minus this. So which is 1 minus zeta. So that is equal to 1 by zeta. So this is basically divided by zeta. And if I put in the value of a here, this will result in the following. This implies a is minus 1 by k square zeta is equal to k square by psi. Therefore, I'm just rubbing this.
Sir?
Just a minute. Okay, shown.
Yes, sir.
Just a minute. And let just let me finish, then I'm coming. This will give us B equals. So I have A is equal to minus 1 by k square, and B equals from here to be minus 1 by k to the power of 4. I think that's found it out correctly. B is minus 1 by k to the power of 4, and then this is multiplied by theta. Right. Well,
Sir, how are we writing minus bk square by xi?
by what?
Uh, I mean, it was bk square into 1 minus xi. How are we writing by xi?
Which equation? This equation. You mean to say I've done some mistake in algebra? Maybe I've done some mistake in algebra. Let me just check.
Sir,
Just,
have
just,
we replaced? Okay.
just a minute. Theta is what? Theta is 1 minus xi into xi. This will give us 1 by k to the power 4. We have got the minus sign, so this is 1 minus. Let me just check with my. I think I have done the calculation correctly. Now tell me which step?
You wrote that minus bk square into 1 minus zeta
I have
plus a zeta equals to 0. I mean,
yes.
so you are replacing 1 minus zeta by 1 by epsilon.
1 by xi, 1 by this.
Okay. Okay,
That,
sir. Okay, sir.
that because zeta is 1 minus 1 by xi. I have just
Okay, sir.
substituted zeta is 1 minus 1 by xi.
Okay, sir. Okay, sir.
Okay. So now
Okay, sir.
what can we see? What is the lesson that we have learned? What we have learned is the following. You have determined the photon propagator. At least you know what you have a solution for d mu tilde k. Because a is minus 1 by k square and b, this is this. So let me just write it down in a nice way. D mu k, that is equal to a is minus 1 by k square plus that theta mu plus b is basically 1 by k to the power of 4, 1 minus xi, 1 minus xi e mu. Yes.
So, if you are comparing coefficient theta lambda,
Ah,
so theta lambda is basically a particle vector.
right.
That is 0 for lambda not equal to
For lambda?
not equal to.
Yeah.
Right. So, isn't that like you are comparing two things on both sides of the equation?
Don't think in terms of that. When I'm writing, this is a covariant notation. That is the power of covariant notation. The entire philosophy of doing the calculation in the covariant notation is this. That you want to write. See, once we are using this lambda mu notation, then you should not revert back and think, okay, what will happen when lambda is equal to mu, where lambda is not equal to mu. That is
But then that doesn't seem to be consistent.
no, it will be consistent. You write down the equations, everything will be consistent. Has to. You write it down. If you have a doubt, you write it down and see what happens. It has to be. There is no other way. That is the power of using this. Otherwise, why would have you done all these things in the first place? You could have done in component notation. Everything in component notation. Like if you look at Maxwell's book on a treatise on electrodynamics or electromagnetic theory, 2 volumes. So what does he do at that time? He writes divergence of B. Nowadays we are smarter and we are writing del dot B. He's writing each of the equation del Bx, del x plus del By, del y. So del B. Those notations were big. The entire philosophy of using covariant notation is that you don't need to write and check it in component form. Component form, if you do the same thing, you will get the same answers. Absolutely, there is no other way out. That is why you are sure that once you do it in this notation, everything will be fine. Okay. So the main takeaway lesson from this is the following: that you now indeed have a consistent solution for this dv in the here, and to simplify this further, what we shall get is the following: minus between minus 1 by k square continue. Then I have minus 1 minus 5 Since this question has come to your mind, I would urge you to go and check. I am not going to do that check because I have done it several. Go and work it out. That will clear your confusion. So you can see that you can write the propagator in a neat way. But I should not call this propagator at this stage because I have not told you. This is just a magic that I have shown you. What I have just shown today is simply the fact that if you modify this equation by a 1 minus 1 by xi factor, then you get a consistent solution. Otherwise, you will not get a consistent solution. And this fact is reflected again. See, what happens if you take xi goes to infinity? Then this factor is 0, 1 by xi. Xi goes to infinity means this is 0. So this equation goes back to the earlier form. And therefore, you know in the earlier form there is no propagator. See what happens here? Xi is infinity. So this makes no sense. So you don't have a propagator. So it is only for any value other than xi is equal to infinity that you have a consistent solution. And in fact, what you can do is, just as Soham mentioned online, that this term is creating a trouble, right? So you said that k nu k lambda is
Yes, sir.
right? So if you get rid of this term, then the trouble is gone. And you can see it from here. You put xi is equal to 1. Xi is equal to 1 means this term is 0. So there is no k nu k lambda term. And then you have a consistent solution. And then what is the propagator? It is just eta mu k square. For xi is equal to 1. So xi is equal to 1. This particular thing, I'm not using the word gauge fixing at this point. I will show it tomorrow in tomorrow's lecture. This xi is equal to 1 is said to be the Feynman Petov gauge. Feynman gauge. Xi is equal to 1. Number 1. And you can use other gauges also. If you put xi is equal to 0, then this does not get rid of this term. But the propagator, you have a value of this propagator for xi is equal to 0. And that is the following. It is basically minus this eta mu minus k nu by k square. So this particular term is not there. Xi is equal to 0. And xi is equal to 0, this is called the Landau gauge. So you can work in different gauges, but I don't want to use the term gauge at this point because I have not given you a justification for modifying this equation in this manner. In the next class, I will tell you why did I modify this equation in this form. The modification of this equation by this factor is precisely due to the fact that we have done a gauge fixing in the action. We have fixed the gauge, and that is the reason it gives rise to a term like this. This calculation we shall do tomorrow. So it is not that. So what it basically does is when you gauge fix, it gets rid of the unphysical degrees of freedom that you have in the program field. So now you have only the transverse, not the longitudinal and the time line program. And once you get rid of the unphysical degrees of freedom, then you have a perfectly fine photon propagator with which you can work. There is one subtlety that you may ask. See, this is the form of the propagator, and I'm just giving you the answer ahead, but I shall show you the calculation tomorrow. This psi is a parameter that comes from gauge fixing. But then you may ask, okay, then there is a problem because propagators will enter into various cross sections, into various Feynman diagrams. Then it seems that this gauge parameter is also entering into that diagram, to that Feynman diagram. But it turns out that if you keep this parameter psi, you do the calculation, at the end of the calculation, the psi parameter will get cancelled out. So the result is gauge invariant. It does not depend on the, it should not depend, the cross section should not depend on which gauge you are. So if you do the calculation between this psi, it will get cancelled out in the final result. It does not figure or find its place in the final result. So let us finish today at this point. We shall continue tomorrow from this place. So does anyone have any question on the online people? Huh?
No, sir.
Okay.
No, Professor.
Okay. Okay. So let me just finish the class here today.